Hi everybody, this video is going to be about molar conversions. We're going to be using dimensional analysis to do the same types of conversions we've done before, but this time instead of using things like inches and feet or minutes and seconds, we're going to use some units that are a little more applicable to chemistry. We're going to be using things like molar mass, the mole, grams, stuff like that. So first, let's start by talking about something called the mole. You may hear it called Avogadro's number. The mole is 6.02 times 10 to the 23rd, and we use this all the time in chemistry to count how many atoms we have at a time. Because atoms are so tiny, we're not going to be counting or weighing out 1 or 2 or 10 atoms at a time, not even 1,000 or 1,000,000 at a time. We're going to be weighing out bazillions at a time. So we're going to use this really big, large number to count our atoms. No, you do not have to copy all those zeros down. You can clearly see why we like scientific notation, because I don't know about you, but I don't want to have to write all those zeros. Okay. So I like to just give you a couple of comparisons because this number is so large that our brain can't actually wrap, our mind around it. It's a pretty big number. So if you had a mole of soda cans, it would cover the entire surface of the earth over 200 miles deep. That's how many soda cans you would have. Instead, let's use something smaller. If you had unpopped popcorn kernels spread over the entire United States, little teeny tiny popcorn kernels, unpopped, it would still be 9 miles deep. That's how big that number is. Instead of objects, since that's clearly not very practical, okay, let's say you were to count to a mole. If you were to count to a mole as 1, 2, 3, 4, 5, 6, 7, 8, 9, it would take forever, right? So instead, let's count in big chunks. Let's count in, increments of 10 million every second. So every second, you're going to count by 10 million. So 10 million, 20 million, 30 million, 40 million, 50 million, 60 million, etc. If you counted nonstop, no bathroom break, no stopping for a snack, no taking a nap, nothing. You counted 10 million every second, it would still take you 2 billion years to count to a mole. That's how big that number is. And that also gives you an idea of how small an atom must be, because 1 mole of atoms is not very big. I can hold a mole of atoms in my hand. A mole of carbon only weighs 12 grams. A mole of hydrogen only weighs 1 gram, right? So atoms are so small, which is why we count them in such big increments. So molar mass is how much 1 mole of something weighs. We're going to be using our periodic table. An atom of hydrogen weighs 1.01 AMUs. AMUs is atomic mass units. You can see here it's a very tiny number of grams. A mole of hydrogen, strangely enough, weighs 1.01 grams. An atom of carbon weighs 12.01 AMUs. A mole of carbon weighs 12.01 grams. So as you can see here, the reason why we picked the reason why, Avogadro picked such a strange number, such a random number to be a mole, was because it allowed us to use our periodic table, and every number on there for mass can either imply that it's the mass of 1 atom, and the unit would be AMU, or you can use the exact same mass number and have it be grams, and then that's how much a mole weighs. So if he picked any other number, this wouldn't have worked out. We would have had to manually do dimensional analysis and converted between AMUs and grams every single time. So this made our life so much easier. So for example, a mole of oxygen weighs 16 grams. A mole of magnesium weighs 24.31 grams. One thing that you will notice is that you want to use the decimal version on the periodic table because, when we're scooping up a whole bunch of atoms at one time, we're going to have a whole mix of different isotopes. So we got to use our average mass because we just don't know which isotope we're going to have. So if we want to count or calculate what the molar mass is, and there's more than one atom, you're going to have to just add together your individual masses. Carbon dioxide is not on the periodic table, but carbon is and oxygen is. So I can find the mass of carbon and add in 2 oxygens. So 12.01 plus 2 times 16. And I find out that 1 mole of carbon dioxide would weigh 44.01 grams. The way we write our units, because nobody wants to have to write this out in words like this, we just write G/MOL. That's not a typo. MOL is actually the abbreviation for a mole. It's not much of an abbreviation, but it technically is an abbreviation. So grams per mole is the unit for molar mass. And if you notice, that kind of looks like a conversion factor, doesn't it? We're going to use molar mass as a conversion factor. We're going to be able to convert back and forth between grams and how many moles it is. So that's going to be a very helpful thing for us. One thing is you got to be a little bit careful with parentheses. So for example, you can see here that we have 2 because we have parentheses here. We have to distribute. We have 2 nitrogens. We have 8 hydrogens. We only have 1 sulfur because it's outside the parentheses. So I find those masses on the periodic table. I add them up. I punch it into my calculator. And I find out that the molar mass of ammonium sulfide is 68.17 grams per mole. People are always going to ask me, what should I round to? How many decimals should I do? Technically you should use significant figures, right? If you want to be technical about it. I kind of don't worry that much about it. In AP Chem, yes, we got to be a little bit more careful. If you go to 2 decimals, that's typically safe. Depending on what the mass is, you may see me round more or less. It's not a big deal. If you get a question and you round a little bit differently than I did, I will still accept your answer. Or if it's multiple choice, the answers will be so far away from each other, it'll be pretty obvious. Like the answer choices for this question maybe were 17, 68, 147. Well, clearly 68 is the correct answer. So don't get too hung up on the rounding part. So molar conversions are conversions that are related to moles, exactly like what it sounds like. We are still using dimensional analysis. One of the things that's actually nice about molar conversions is your pathway is very limited. On the earlier types of dimensional analysis problems we've been doing, you had so many options to choose from, so many different conversion factors and pathways you could take. But for molar conversions, this is your only set of pathways that you can use. You can go from grams to moles. You can go moles to molecules. You can go backwards. You could go molecules to moles or moles to grams. But you cannot do something like go from grams directly to molecules. We do not have a conversion factor for that. We're going to be using little baby steps like our frog hopping on lily pads to get to the other side of the pond. So to go from grams to moles, or vice versa, you'll use molar mass. Remember, molar mass is different depending on which molecule you're using. So it'll have some number of grams over 1 mole. By definition, molar mass is how much 1 mole of something weighs. So the X here can change based on the formula, but the 1 mole has to stay the same. It's always going to be 1 mole. That's like saying 1 dozen is 12 donuts. By definition, that's how many are in 1 dozen. To go back and forth between moles and molecules, you'll use Avogadro's number. 6.02 times 10 to the 23rd molecules per 1 mole. It has to be a 1, you can't change that. If you want to be a little more generic, instead of saying molecules, remember you can say particles. So if you want to be more generic, maybe instead of molecules you have atoms, for example, you would just say particles or swap it for the more specific unit. But usually we're doing molecules in a chemistry class. So for this example, we're trying to figure out how many grams does 1.7 moles of sodium chloride weigh. So my pathway is picked for me. I don't get to do anything different. These are my only options. And I'm going to go from grams to moles. So I don't even need the molecule part. It's just one simple single step. We will need molar mass. So I need to look at my actual formula for sodium chloride and figure out that the molar mass is 22.99 for sodium. And I'm adding in the mass of my chlorine, which is 35.45. When I add those together, I get 58.44 grams per mole. Remember that I'm getting these numbers from the periodic table. That's where those numbers are coming from. So now this is my conversion factor. My molar mass becomes my conversion factor. So I start with my known value. I'm going to use my line method. I'm going to see that I'm trying to cancel moles. So 1 mole goes on the bottom. By definition, molar mass is how much 1 mole of something weighs. And because it's sodium chloride, I'm going to have 58.44 grams on the top. My moles cancel. I'm left with grams. I punch that in my calculator, and I get 99.35 for my grams. This time, let's try going backwards. Let's start with grams and go to moles. So I have my molar pathway, but I'm only going to use this portion. This time I'm going from moles to grams. I still use molar mass. This time it's the molar mass of carbon dioxide. So here I use my periodic table. Here's my mass of carbon. And here's my mass of oxygen. And I have 2 oxygens here. So I add that up. 44.01 grams per mole becomes my conversion factor. I start with my known value. I want to cancel grams, so this time the 44 is going to go on the bottom and 1 mole goes on top. By definition, molar mass is how much 1 mole weighs, so I have to make sure it's a 1 there. Grams cancels, I'm left with moles, punch it in my calculator, and I find out if I had 14 grams of carbon dioxide, I really have 0.32 moles of carbon dioxide. Let's try moles to molecules. Here's my molar pathway, but this time I'm only going to use that part. When I go moles to molecules, I'll use Avogadro's number. The nice thing about his number is it's always the same. With molar mass, I have to change it each time depending on the formula, but Avogadro's number will always be the same. I start with my known value. Because I want to get rid of moles, I'm going to put 1 mole on the bottom. And I'm going to have Avogadro's number on the top. Because it's water, I am going to say molecules. You could say particles if you want to be more generic. That's always fine. I punch that in my calculator. And I'm going to get that 5.3 moles of water has 3.19 times 10 to the 24 molecules in it. Let's go the opposite direction. This time molecules to moles. I'm still going to use Avogadro's number. It's not going to change. I start with my known value. It's okay that it's scientific notation, it doesn't matter. If I want molecules to cancel, I'm going to need to put Avogadro's number on the bottom, and 1 mole will be on the top. Molecules will cancel, I'll be left with moles. If you do this correctly and you use the parentheses correctly, this is the number you will get. You have to make sure that you put parentheses on the bottom of that fraction to keep your scientific notation on the bottom. If you're not careful in your calculator, it's going to get confused and it's going to think this times 10 to the 23rd should be on the top, which is not correct. We don't want that. We want to make sure that our parentheses keep it on the bottom. If you ever get a number that seems way too big compared to what you should have gotten, then that's telling you that you probably forgot your parentheses. That is probably the #1 mistake we see all school year. All right, now let's go from grams to molecules. Here's our molar pathway, but this time we are going to have to use the entire thing. We're going to use molar mass first, then we're going to use Avogadro's number. This molar mass here is the molar mass of water, H2O. I got that from the periodic table. 2 hydrogens plus an oxygen. Start with my known value. I want to get rid of grams. So my 18 is going to go on the bottom. For the sake of space on this PowerPoint, I'm just going to put 18. I'm not going to put 18.02. It's not a big deal. Remember, we don't care too much about the decimals in this class. The 1 mole goes on the top. The units cancel. So now I'm going to get rid of the moles by putting 1 mole on the bottom. Avogadro's number goes on top. Moles cancels. I'm left with molecules. Punch it in my calculator, and that's the answer that I get. Going from molecules to grams, once again I'm going to have to use the entire molar pathway, but this time I'm going backwards. Molecules to moles, moles to grams. I'll use Avogadro's number first, then I'll use molar mass. This time it's the molar mass of CH4. If I look on the periodic table, carbon weighs 12. I have 4 hydrogens that each weigh 1, so I get a mass of 16. I start with my known value. Avogadro's number comes next. To get rid of molecules, it's going to go on the bottom. 1 mole is going to go on the top. Molecules cancels. I'm going to then use molar mass, which is 1 mole on the bottom, 16 on the top. That way moles cancels. I'll be left with grams. Because we have that scientific notation on the bottom, we have to be really careful that we're using our parentheses in our calculator. We want to make sure that we keep that 10 to the 23rd down on the denominator. We don't want our calculator confused and flipping it up to the top. So if I have 2.6 times 10 to the 25 molecules of CH4, it would weigh about 693 grams. And just a little reminder that you can be generic, you can use particles instead. So Avogadro's number, instead of using molecules, it could have been particles, it could be atoms, it could be soda cans, it could be cars. It doesn't really matter what you're counting. It's just talking about whatever item it is that you're counting. Alright, that's it for this video. I hope it was helpful. Bye everybody.